In order to determine if our program of studies has included important mathematics, I referred to John Van de Waal's series on student-centered mathematics. Here are the big ideas he lists. Even though we have specific outcomes that address this big idea, beginning in Division 2 and carrying through until the end of Division 4, I don't think it's emphasized enough that these representations are linked and that certain forms are more helpful in specific situations. For example, at the grade 7 level, where students model and solve problems, concretely, pictorially, and symbolically, using linear equations, I think we have missed an opportunity to emphasize this link. From grades 1 to 9, students progress from the concrete to pictorial to symbolic representations. They learn to recognize patterns, then determine relationships, and develop skills to generalize them. In high school, students focus on graphic and then algebraic representations, which also mirrors this big idea. This big idea is covered in our program of studies. Beginning in grade 3, students begin to use symbols to represent an unknown number in equations, and in grade 5 they learn that a letter is used to represent an unknown number as well. In grade 6, students begin representing generalizations arising from number relationships using equations with letter variables. This work continues through junior high, and starting in Math 10C, students learn that slope represents a rate of change. Despite the fact that these three different contexts are included in our curriculum, I don't believe that it has been made explicit for teachers or students through grades 1 to 12. For example, I don't believe that grade 6 teachers would understand that they have to explicitly point out that students have been using variables to represent one number, and that they're beginning to use variables as placeholders in generalized expressions or formulas. I'm also sure that 10C teachers explain that slope represents a rate of change, but according to the program of studies, it won't be obvious for them to make connections to the understanding that students bring to high school. This could be a barrier to students because they aren't aware of the different variable meanings. We need to be explicit about the fact that variables are used in different ways in different situations. I think that curriculum writers were trying to solve the problem that students think the equal sign means, give me the answer, by the way specific outcomes have been moved around in our program of studies. For example, algebraic work has been brought down to grade 1, where students learn about equal and not equal in concrete and pictorial situations. Work continues through the end of grade 12 on algebraic concept. Having said this, though, the way that the specific outcomes have been organized and scaffolded leads me to believe that the big idea that 3 plus 8 and 5n plus 2 are equivalent expressions may not be achieved. I think there needs to be a more deliberate explanation for teachers or some additional specific outcomes about treating expressions as single quantities or objects to which we can apply operations. Students need to spend more time on this concept. Students in grade 6 begin learning about the idea of functions, but at an introductory level. A little more work is done on this concept in junior high, but is not a major focus. Functions and relations become very important in high school, and this concept is included there. This big idea is also included in our program of studies at the high school level, where students extend what they know about equations to functions. 10C is where students formally learn about functions even though they've seen them since grade 6. They learn to describe relationships verbally, algebraically, graphically, pictorially, concretely, and numerically. Our program of studies outlines the expectation that students need to understand that these different representations are connected and illustrate the same relation. It does not, however, include the idea that each representation provides a different view of the function, each highlighting a different perspective which offers insight into certain characteristics of the situation or generalization. Unless a teacher makes these things explicit, students may not learn how to identify which form is more advantageous than the others in given circumstances. The next component that NCTM suggests is articulation across the grades. They suggest building successively deeper and more refined understanding, a curriculum that provides a roadmap that helps teachers guide students to increasing levels of sophistication and depths of knowledge, and teachers at each level understand the mathematics that has been studied by students at the previous level and what is to be the focus at successive levels. All three of these components exist in our program of studies. There isn't, however, any specific attention to the last bullet. Teachers would learn the mathematics taught at a previous level and what would be coming in successive levels only if they look forward and back on the program of studies. Generally speaking, through grades 1 to 12, students learn to do algebra and then use algebra to learn. Older students extend to new and novel situations and hopefully have a chance to see the beauty in thinking algebraically and how powerful this can be across mathematics and beyond the classroom. Here are some specific examples that demonstrate how specific outcomes in our program of studies move to more sophisticated and deeper knowledge through the grades. There are no specific outcomes that stand alone or come to a dead end as we had in our previous program of studies. For example, students in grade 7 learned about the Monte Carlo method of simulation, and grade 8 students learned about box and whisker plots and the four-color theorem. Students did not see these concepts again and didn't explore them to a deeper level. One area, though, that seems a bit weak or disconnected is the concept of inequalities. Students learn about inequality concretely in grade 1 and then begin using the greater than or less than symbols in grade 2. Students don't see this concept again until grade 9, when they explain and illustrate single variable linear inequalities with rational coefficients. Then students see inequalities in Math 20-1, where they solve linear inequalities with one variable and then learn how to solve linear and quadratic inequalities in two variables. My belief is that if we can support students learning through the 7 process skills, we help them take their learning to a deeper level. So teaching deeper means that students have a chance to organize and strengthen their math thinking through various forms of communication and be able to explain the strategies used, make connections among math concepts and apply them to contexts inside and outside of class, develop flexibility with numbers and personal strategies that support mental math and estimation skills, build new math learning through problems as they learn to apply a variety of strategies, justify and defend their math conjectures in a variety of ways as well as critique others' arguments, choose suitable tools to explore, study, solve problems, and analyze math concepts, and progress from concrete math experiences to learning how to draw visuals and symbolically represent these ideas and situations to convey meaning. A challenge around teaching through the process skills is that many teachers don't have experience with this type of pedagogy. Teachers don't necessarily have the conceptual understanding to be able to offer classroom experiences in a variety of ways to meet the needs of all the students in a classroom setting. The illustrative tasks that I've created at the end of this presentation will give examples of how to integrate these process skills into specific outcomes relating to algebra and how to teach the outcomes deeper. For the next section, where I present 2 illustrative tasks that help students learn an algebraic concept more deeply, I first clarified what a high-level mathematics task was. I referred to NCTM's description. A high-level mathematical task is not the same as a difficult task. High-level tasks offer multiple entry points, opportunities for students to begin working on the task using a variety of approaches and techniques. High-level tasks promote thinking, reasoning, and mathematical sense-making. High-level tasks are not simply reproducing memorized facts or applying learned procedures. So for my first task, I chose a grade 6 activity. So to situate you where students are for this particular activity, students will already have experience with these outcomes. They'll have worked with graphs and tables. They will have worked on developing relationships, learning how to represent generalizations, and express problems as equations with a letter variable. In my work with teachers, I have heard many grade 6 teachers struggle with this specific outcome. They are unsure of what it means and then how to present this without telling students what to do. The focus in this activity is working flexibly with whole numbers. So this activity is to be carried out before there's any formal instruction, and it's a guided hands-on exploration. Since it's unlikely that any school would have a class set of these number balances, I would model this activity with the entire class and have various students help out. Then I would have students do this activity in partners using their own values, perhaps as a station. After this, we'd create sketches to represent our thinking and connect the visuals to the concrete representations. After many such activities and drawing the scales, I would introduce the symbolic notation. I would scribe what it would look like and help students make the link between the concrete, pictorial, and symbolic notation. I'd ask students to choose a number and model it in different ways on the number scale. We are getting at the concept of equations being equivalent, but not identical. Then I would ask students to add a number of their choice to the left-hand side and ask them if the scale is balanced. If it's not balanced, what do they need to do to make it balanced? Discuss what they notice. As a teacher, observe whether they have to count, or do they understand that it doesn't matter what is on the number balance. If you add 5 to one side, all you have to do is do the same to the other side, which is an algebraic strategy. Then I would talk to students about last time you added 5 to both sides and the scale was balanced. Could you add 5 to both sides again, but show the number 5 differently and ask what they notice? So here's an example where they add 5, but it looks different on each side. You can add the same value to each side, but it can look different, which is a focus on equivalence again. Now we are beginning with a more complicated representation, and we'd move into subtraction. Can you take off one number from each side and still have it balance? Students might notice that there's a 6 on both sides, so they can take off the same number from each side and still maintain balance. Now, can you take off one value from each side in a different way and still keep it balanced? Here they can take off 8, but it's shown in 2 different ways. After exploring a bit with addition and subtraction, I would ask students if there were any other operations that could work in this way. In other words, is there a different action we could take on both sides that would maintain balance or keep the equation balanced? I'd hope that students would think about multiplication and division and figure out how they could represent this on the number balance. If students needed support, I could ask them, how would you double 6 plus 4 is the same as 3 plus 7? Here you can see that I can lead students towards the idea of collecting like terms, which is important work through junior and senior high. This leads us to using distributive property. We could also consider using the order of operations, which students learn in grade 6. Then students could halve, or divide by 2, their representation. They have to take half of everything, not just one of the numbers. After this, students could be asked to triple the initial value and then take a third of it to reinforce this concept. I would let students spend a lot of time with the number balances. I want them to understand that when we add, subtract, multiply, divide by the same value on both sides, that the equation is still balanced and has the same solution. If we take different actions on each side of the equation, it is no longer balanced. As far as follow-up activities go, we would consider drawing to represent our concrete experiences and thinking. Then I'd encourage students to use drawings to help them think without the concrete experiences. I would assess students' performance only concretely and pictorially. I would still lead students to the symbolic notation, even if it is beyond the curriculum. I believe this is a high-level task and it takes students deep into the outcome. It offers multiple entry points and opportunities for students to begin working on the task. This would be an appropriate difficulty level for all students no matter how they approach the task, whether it was arithmetically, pre-algebraically, or algebraically. As well as they work, students must think, reason, and make sense of the math they are doing. This activity and follow-up work gives students the chance to begin thinking about expressions as objects or single quantities that can be operated on, that they can prove equivalence without doing all the arithmetic. In addition, the activity embeds the 5 process skills indicated in the specific outcome. Students must communicate while they work. They make connections within mathematics they already know about the basic number operations and their experiences with the balance scale. The activity is presented in a problem-solving context, not offered as step-by-step instructions. Students must analyze what works and what isn't working as they manipulate the materials, and as they are working concretely, they are able to improve their visualizing skills so that eventually the balance scale can be removed, and students will be able to picture the scales in their minds to think algebraically. The next activity I've chosen to do is a Math 10C activity. The background that they'll already have: they will have worked on relationships among data, graphs, and situations. They've been introduced to relations and functions. They have an understanding of slope. They can describe and represent linear relations, and they can determine the characteristics of the graphs of linear relations. As well, they're familiar with the 3 forms of notation. They can determine the equation of a linear relation to solve problems, and they can represent a linear function using function notation. This is the focus. Students will learn several methods to solve systems of linear equations and develop the habit of looking at the equations first before deciding on a particular method to use. This activity is carried out before any formal instruction, and it's presented as a problem. Give each pair of students 2 recipe cards. 1 linear relation is written on each recipe card. On the cards, there will be 3 forms of equations. The pair of students work together. They look at their 2 equations and answer the following questions. Students must manipulate the equations so they can compare them and be able to draw graphs. Students all have a partner, so even if they are struggling, there will be someone else to work with. After their work together, the students will share their observations and conclusions. They'll make connections between the types of equations and the number of solutions found. The teacher summarizes the big ideas, and the phrase will be introduced, solving a system of linear equations graphically. Follow-up activities. Give students more time to become comfortable working with the systems of linear equations graphically. On a different day, hand out the same linear equation cards to different pairs of students. Do the same activity, but this time tell the students that they cannot draw their graphs. Their challenge is to figure out how to determine whether their systems of equations have 1, none, or infinite solutions without drawing the graphs. And then the teacher will introduce the phrase, solving a system of linear equations algebraically. I believe that these are high-level tasks that help students learn about systems of linear equations at a deep level. Students can begin working on this task in many different ways. They are also working collaboratively so they can learn or receive support from their partners. Since this has been given to students as a problem with no specific direction, students must consider various strategies. As they work together, they are making sense of the math they are learning together. In addition, the activity embeds the 5 process skills indicated in the outcome. Since students are not given instructions to do this, they must make connections to what they already understand about linear equations and their corresponding graphs. The activity is presented as a problem and not offered as step-by-step directions. Students must analyze what works and what isn't working to answer the teacher's question, and hopefully create some of their own extension questions. Students would probably choose a tool, some sort of technology, to calculate and plot the points, and as they are working, students are seeing what the graph looks like and what appears when there are 1, infinite, and no solutions to these systems. After studying the variables and equations and relations and function strands from kindergarten to grade 12, I believe that our current program of studies is well designed to meet the goal of teaching less but teaching deeper. As teachers and students learn together with this revised program of studies, I'm sure we'll find areas that need improvement, but overall we have a curriculum that is coherent, focused on important mathematics, and is well articulated across the grades.